Well, we're up to week number 7 on electromagnetic induction. This is in the textbook, chapter 29. And here's the meaning of the subject, electromagnetic induction. When a magnetic field changes in time, there exists an associated electric field. Now, so far we've only considered fields that do not depend on time. We started with electrostatics. Then we considered magnetostatics, magnetic fields that don't depend on time, produced by constant currents. Well, now we're considering something different. The magnetic field depends on time. And when that's true, there must exist an associated electric field. So here's the outline for the screencast. This is part 1 of the screencast. First of all, a kind of historical introduction on Michael Faraday, the great scientist of the 19th century, who discovered electromagnetic induction. And Faraday's law is the mathematical equation that describes electromagnetic induction quantitatively. And then, well, there'll be one application, the electric generator. So we'll start with a little history of the subject. And it goes back to discoveries by the great Michael Faraday. Michael Faraday discovered electromagnetic induction in 1830. And he had been working on this for about 10 years. He had been trying to produce an electric field from a magnetic field by experiments over a period of 10 years without success. But finally, in 1830, he was successful. Now, we shouldn't forget that electromagnetic induction was also discovered independently by Joseph Henry in the United States. Joseph Henry was the second great physicist in America. The first was Benjamin Franklin, and the second was Joseph Henry. But in 1830, he was just an obscure colonial, he was an obscure, not colonialist at that day, but kind of an obscure, he was a high school teacher in Albany, New York, kind of in the American frontier. Later, he became very famous. But Michael Faraday worked in London, and he was very well known in science and in physics. So he's usually given the credit for the discovery of electromagnetic induction. Faraday observed that when a current in a coil of wire changes, then another current is induced in another coil of wire. The two coils are not connected. The interaction is purely a field effect. The current in the first coil of wire produces a magnetic field. Now, if the current changes, the magnetic field changes. And when a magnetic field changes, there exists an associated electric field. So there'll be an electric field present in the other coil of wire. And we know that when there's an electric field in a metal, in a conductor, there's electromotive force, and it'll induce current. So the interaction between the two coils of wire is really a field effect. And here are a couple of equations that will be relevant. The electromotive force around the second coil of wire. So here we have one coil of wire. And here we have another coil of wire. So this is coil number 2. This is coil number 1. And there's some sort of electromotive force producing a current in the first coil of wire. So there'll be a current here, I1. Now, as we know, the current creates a magnetic field. So let's put it in a different color. There'll be a magnetic field. And we could call that B1, because that's the magnetic field produced by the current in the first coil of wire. Now, the flux through the second coil is phi21. So there's a flux through this second coil of wire. We'll call that phi21. So phi21 is the integral B1 dot A through the surface 2. So maybe I should call this dA2. That's phi21. And now what Faraday's law says is that there's an EMF around coil 2 that comes from the rate of change of the flux through coil 2. So the EMF through the second coil of wire is minus, that minus sign will be important, d phi dt. Now what's EMF? Sometimes we write this as script E. That's the EMF around the second coil of wire. Well, that's the line integral of E dot ds around the second coil of wire. So that's called the circulation of the electric field for the second coil. In other words, there's an electric field in the second coil of wire. And you know, if I integrate the electric field times the distance, I get the voltage. So this is the voltage around a coil of wire, or the electromotive force within that coil of wire. And that will, of course, create current in the second coil of wire. So I1 does not produce I2, but a changing value of I1 will produce a changing flux, and that produces the electromotive force and the induced current in the second coil. This is not just some obscure laboratory effect, although when it was discovered by Faraday, it was an unknown laboratory effect. But today, this is the phenomenon that we use to create the alternating current electricity that we use every day. So this little field effect makes possible the advanced technology that our society depends on. I mean, ask yourself, why is there an alternating electromotive force, a voltage, 120 volts alternating, in every wall socket, in every room in your house? And of course, the answer is the wires behind the wall, which of course you can't see because they're behind the wall, but they're connected to a huge network. And on that network, there's somewhere an electric generator, which provides an alternating EMF. And that alternating EMF spreads throughout the network. This network, covers a whole city. And how does the electric generator do that? Well, it's by Faraday's law. Well, here's a little bit more about Michael Faraday and the discovery of electromagnetic induction. Faraday started out with a wrong idea. He started out with the idea that if there's a magnetic field, there should be current. Because he already knew from 1820 that current creates a magnetic field, he sort of had the idea that a magnetic field should be able to create a current. Well, that's not quite right. But what he noticed after many experiments is that when the magnetic field changes in time, there's a little pulse of current created in a nearby coil of wire. So it's not the magnetic field, it's the time dependence of the magnetic field, which creates electromagnetic induction and induced currents. Here are some of the, here's a photo. Faraday was, there are photographs of Faraday. This is a drawing. Faraday had an iron ring, a big iron ring, and two coils of wire wrapped around the ring. And what he noticed is that if he turned on current in coil A, he would observe for a brief instant a little bit of current in coil B. But it was a transitory thing. It only happened when there was a time dependence. Here's one of his demonstrations, another one of his demonstrations. This was his first demonstration. Here's another one. He had a coil of wire attached to a battery. So here's a coil of wire attached to a battery. And he had a magnet which he could move in and out of the coil of wire. Actually, an electromagnet. And when he moved the magnet, there would be an induced current in the second coil of wire. Now, I guess this isn't a battery. This is just a galvanometer. So here's a galvanometer to observe current, like an ammeter. And here's the battery. So the battery produces a magnetic field. If the magnetic field changes inside the coil of wire, the galvanometer indicates, briefly, an electric current. Or here's another example, again showing a large iron ring. The purpose of the iron was to increase the strength of the magnetic field. So it's kind of a small effect, but it can be multiplied many times by enclosing the coils with iron. So if he closed the switch on the primary coil, that generated a magnetic field in the iron. Well, in the brief period of time when the magnetic field is changing in time, turning on, there'll be a current observed in the secondary coil. All right, so this started out as a kind of laboratory effect, but electromagnetic induction is the physical phenomenon that we use to generate alternating current electricity, which is the basis for our technological society. So here's another picture. This doesn't have to be an electromagnet. It could just be a permanent magnet. It could just be a bar magnet. So suppose you have a coil of wire, a bar magnet, and a galvanometer. The galvanometer is attached to the coil of wire. A galvanometer is like an ammeter. It measures current. It's just a measuring device. It measures current. Now, if the magnet is not moving, there won't be any current, and the galvanometer needle will point to 0. But if the magnet moves towards the coil of wire, the galvanometer needle will be deflected, indicating some current has occurred in the coil of wire. Or if the magnet moves away from the coil of wire, during the time that the magnet is moving away, there'll be a little current, indicated by a deflection of the galvanometer needle. As long as the magnet is not moving, there is no current, and the galvanometer points to 0. But when the magnet moves, the galvanometer needle will be deflected one way or the other. The current in the coil of wire is really a secondary effect. The primary effect is that a time rate of change of a magnetic field, which occurs if the magnet moves towards or away from the wire, since the magnetic field is strongest near the poles of the magnet. If the magnet moves, then the amount of flux, the amount of field going through this area, will change. The magnetic field will change in this area. And that creates an electric field. Now, one of the interesting characteristics of electromagnetic induction is that the electric field curls around the change in the magnetic field. So the induced electric field, well, it'll either be clockwise or counterclockwise, depending on whether this magnet is moving towards or away from the coil. But if the change of magnetic field is in the z direction, then the electric field is curling around in the xy plane. Now I say there's a secondary effect, the current in the coil of wire, which is what we observe in the galvanometer. That's a secondary effect because it's driven by the electric field. The electric field is the primary effect. The current is kind of a consequence of the primary effect. The direction of the electric field is interesting and a little complicated to understand. The induced electric field curls around the change of the magnetic field. So here's a little picture where there's a magnetic field, put that in blue. So there's a magnetic field pointing away from you. The little X's here are supposed to indicate the back end of a vector. So vector back end, that's where the feathers would be in the arrow. That's in the side closest to you. So the magnetic field is pointing away from you. Now let's suppose that that magnetic field is increasing, becoming stronger. Then the induced electric field will be this direction. Put that in a red color. The electric field is only present when the magnetic field is changing. But if B is increasing, that is, it's getting stronger, then the electric field will be this way, counterclockwise. Now, suppose the magnetic field is not increasing, but it's decreasing. Suppose the magnetic field is getting weaker. Then the current will be clockwise. So when there's a changing magnetic field, there's an electric field that curls around the direction of the change. But is it clockwise or is it counterclockwise? Well, that's a little bit tricky. The EMF is minus d phi dt. And you see that minus sign. So if the magnetic field changes in the direction away from you, then the flux is changing in time. But the EMF is the negative rate of change of the flux. That means the EMF is counterclockwise. It's sort of the opposite of the right-hand rule. If the change of B is away from you, let your thumb point in the direction of the change of B, the thumb of your right hand. Then you notice that the fingers curl clockwise. But the EMF is the negative rate of change of the flux. So the electric field will be counterclockwise. This is sometimes called Lenz's law. The electric field curls in a direction that opposes the change of the magnetic field. The EMF is minus d phi dt. So if a conductor were present here in this blue region, then the EMF would drive a current in this direction, counterclockwise. Well, that current, by the right-hand rule, produces a magnetic field pointing out towards you. So if a magnetic field pointing away from you is getting stronger, then there will be induced a current that produces a magnetic field out towards you, which is opposing the change of the magnetic field. The magnetic field wants to become stronger in the away direction, but the induced current creates a magnetic field in the towards you direction. Of course, that current only exists if there's a conductor present. But if a conductor is present, then the induced current produced in the conductor produces a magnetic field in the opposite direction, opposite to the change of the applied field. And that's called Lenz's law. Electromagnetic induction opposes the change of the magnetic field. And it's a little tricky because it's really a right-hand rule with a negative sign. Now, I tried to emphasize, if there's no conductor present, there's still an electric field induced, because this is purely a field effect. But of course, that wouldn't create any current because there's no conductor present. So if this blue region were just vacuum, and you increase the magnetic field pointing away from you, you made it more strong, there would be an induced electric field, but there wouldn't be any current because a current requires a conductor. So the direction opposes the change of the magnetic field, but if there's no current, there's nothing producing opposition to the magnetic field. So it's a little tricky well, the main thing is to remember this is purely a field effect. Well, I explained electromagnetic induction in qualitative terms. When a magnetic field changes in time, an electric field exists. And the electric field curls around the change of the magnetic field. Now I want to start writing down equations which will describe this phenomenon quantitatively. And that those quantitative equations are called Faraday's law. Faraday's law can be written in different ways. It can be written as a differential equation, partial differential equation, involving derivatives. In differential form, Faraday's law says the curl of E is minus dB dt. So on the right-hand side, I have the rate of change of the magnetic field, a vector, times minus 1. That has to be equal to the curl of the electric field in space. So that's why you say the electric field curls around the change in the magnetic field. Here's a little picture. Suppose we have a magnetic field pointing in this direction, sort of northeast. And let's suppose the magnetic field gets stronger. So there's a change in the magnetic field, also in the northeast direction. Well, there'll be an induced electric field which curls around the change of the magnetic field. So it'll be curling around in the third direction. You know, you've got to view this in 3 dimensions. In the third dimension, there'll be an electric field that curls around with a circulation. And now the question is it clockwise or is it counterclockwise? Well, looked at from this side, what would that be? If we look at it from this side, I guess that would be, if we put our eye down here, so there's our eye looking at the magnetic field pointing away from us and increasing. This direction would be counterclockwise, as seen from that side. Or if I looked at it from this side, if this is my eye, and I looked at it from this side, I would see that direction as being clockwise. So it depends on how you're looking at it. Sort of looking at it facing the magnetic field area, you see the direction is like this. It's clockwise. Seen from the other direction, that corresponds to counterclockwise. And the question of clockwise or counterclockwise has to do with this minus sign. Now, let me review a little bit. Previously, we've only considered time-independent fields. So we considered the electric field independent of time. That's called electrostatics. And there are equations for the field. For example, del dot E, the divergence of E, is equal to rho over epsilon 0, where rho is the charge density. That's Gauss's law as a differential equation. Or we could say the flux of E through a closed surface is the charge enclosed divided by epsilon 0. That's the integral form of Gauss's law. Well, that involves the divergence of E. Now, what about the curl of E? Well, in electrostatics, the curl of E is 0. That's because in electrostatics, we can always write E as minus the gradient of V. But the curl of a gradient is always 0. The cross product of del with del is always 0. It's just like for vectors. The cross product of a vector with itself is always 0 because the two vectors have to cross each other. If they're parallel, or if they're the same vector, then the cross product would be 0. So that's electrostatics. Then we studied magnetostatics, which is a bit different. In magnetostatics, the source is a current, or a current density, and that leads to a curl of B. So the source equation is the curl of B is mu naught J. That's called Ampere's law, where J is the current density. Or the integral form of Ampere's law says the circulation of B around a circuit, around a closed curve, is equal to mu naught I, where I is the amount of current going through the surface bounded by the curve. So we have a flux integral is the charge, the flux integral of E is the charge, the circulation integral of B is the current. Not the current in the closed loop, but the current going through the surface enclosed by the closed loop. Now that takes care of the curl of B. Now what about the divergence of B? Well, in fact, the divergence of B is 0. That's Gauss's law for magnetism, or equivalently, the integral B dot dA over any closed surface is 0. So you see how magnetism is very different from electricity. The divergence of E is the charge density, or the flux of E is the charge enclosed. But the divergence of B is always 0. Or the flux of B through a closed surface is always 0. There are charges that carry the electric field. There are no charges that carry the magnetic field. Such charges would be called magnetic monopoles, and there have been many experiments to search for magnetic monopoles, for particles that carry the magnetic field in the way that charges carry the electric field. And all those experiments have failed, so we now believe there are no magnetic monopoles. Now, this is all for time-independent fields. For the rest of the semester, we'll be considering time-dependent fields. And we're starting with Faraday's law. Given a time-dependent magnetic field, there must exist an electric field, which may be time-dependent. It could be independent of time, but in any case, the electric field must exist if the magnetic field changes in time. And the equations, curl of E is minus dB dt. So the curl of the electric field is the negative of the rate of change of the magnetic field. Now, of course, if the magnetic field did not depend on time, then dB dt would be 0. And then we'd be back to electrostatics, where dB dt is where curl of E is 0. The curl of E equals 0 is only true for static systems. But if there's a time-dependent system, then the curl of E is, well, it could be 0, but it's not necessarily 0. What it is necessarily equal to, it's minus the rate of change of B, rate of change in time. Now, we can also write this equation in an integral form. We can calculate the circulation of E. See, the curl goes with the circulation. So we can calculate the circulation of E. That's the circulation of E around some closed curve. So we have some curve in space. Could be a circle, could be any closed curve. And we calculate the circulation of E around that curve. In electrostatics, that would always be 0. because the curl of E is 0. In magnetostatics, that's the negative rate of change of the flux of B through some surface, any surface, bounded by C. So here's a surface bounded by C. It's this little surface down here. And if we calculate the flux through that little surface, the negative rate of change of that flux, the flux in this direction, I guess, is equal to the EMF, or the circulation of E. All right, so we'll have some homework problems where you have to calculate the electric field due to a changing magnetic field, or maybe vice versa. Given an electric field for which the curl is not 0, what's the magnetic field? Usually we are interested in calculating E from B. So given B, what's E? Now, this is the differential equation written as an equation involving derivatives, the spatial derivatives of E related to the time derivative of B. Or we can convert that into an integral form, the circulation of E around some circuit, around some curve in space. This curve in space is just an imaginary mathematical curve. There's no material there. It's just a curve in space. That's C. And now that's minus d phi dt. Phi is the flux of the magnetic field through the surface bounded by C. It could be any surface bounded by C. And this negative sign is important. So in field theory, we can either use differential equations or we can use integral equations. Now we can write this equation in a simpler form, and this is what we'll usually use in the law and kappa homework. So this is what's often called Faraday's law, and that we will apply in various homework calculations. But this differential equation is also called Faraday's law. You see, the circulation of E around a surface, around a coil, let me say this right. The circulation of E around a closed curve is the electromotive force around the curve. We often use script E for electromotive force. So this side of the equation is the electromotive force, or EMF, around a loop. And that's equal to, don't forget the minus sign, minus d phi dt, where phi is the flux of B through a surface bounded by the loop. So the EMF is equal to the negative rate of change of the magnetic flux through any surface bounded by the loop. Because of the complexities of 3 dimensions, it's a little hard to grasp this. So let's work out an example. Suppose we have B of x of t, which is in the z direction. So this will be the z-axis. And this will be the magnetic field. And suppose that it's increasing in time. So the strength is beta times t. So a little time later, there'll be an additional magnetic field, delta B. So here's delta B. So B depends on time. The z component of B is beta t. So it's increasing in time. We'll think of beta as being positive. For example, beta might be 5 Tesla per second. So somewhere down here we have a source for the magnetic field. Maybe this is a current. A current in this direction would produce a magnetic field in the z direction. And if that current is increasing, the strength of the magnetic field will be increasing. Okay, so that's the problem. Now the question is, what's the electric field? I don't mean the electric field down here. I mean the electric field up here, where the magnetic field is changing in time. So what's the electric field? Well, let's put the electric field in, I don't know, some other color, purple. Now we know there's a changing magnetic field, so there's an electric field that curls around the change of the magnetic field. That will be E. But now the question is, well, okay, so B is in the Z direction, so E will be in the XY direction. E will be in the XY, parallel to the XY plane. But now the question is, what's the direction of E? Well, it could be clockwise or it could be counterclockwise. Which is it? Well, again, using the right-hand rule, the change of B pointing upward, by the right-hand rule, your fingers curl around in this direction, but the induced magnetic field the induced electric field is in the other direction. So the induced electric field will be this way. Seen from below, that would be counterclockwise. Seen from above, you sort of have to visualize this in 3 dimensions. Seen from above, it's clockwise. So the electric field curls around the change of B in the direction given by Lenz's law. And you can see from the picture here, it's azimuthal. It's in the azimuthal direction. It's E phi hat. It's in the phi hat direction. Here's the z-axis. Here's the azimuthal direction, phi. So this is the z coordinate. This is the phi coordinate. The phi coordinate is this way. Wait a minute. E is in the opposite direction. So I'll say E is E phi hat, and when I calculate E phi, I'll find that it's negative. Now, by the symmetry of the problem, there's rotational symmetry of the problem, so the magnitude of E phi can only depend on the distance away from the z-axis. So this distance will be called rho. Rho, phi, and z are the cylindrical coordinates for this problem. So rho is the distance from the center to the point where I'm observing the electric field. All right, so let's write E of x is some function of rho, let's call it f rho phi hat, in terms of the cylindrical coordinates rho, phi, z. So this is z, this is phi, this is rho, pointing away from the z-axis. And z cross rho is phi. Now we'll apply Faraday's law. We'll use the integral form of Faraday's law. First of all, we'll calculate the circulation. And for a circuit, for a loop, we'll just take a circle. So the circulation of E around a circle will be the integral E phi ds is rho d phi. ds is in the phi direction. It's tangent to the circle. So E phi ds phi is E phi, and ds is rho d phi, where phi is in radians. And phi goes from 0 to 2 pi, all the way around the circle. So it's 2 pi rho f rho. That's the circulation. Now what about the flux? Well, we'll take as the surface the disk. We have the integral over the disk inside that circle, b dot dA. Now b is beta t. Doesn't depend on the coordinates in space, so the integral dA is just a. B points in the z direction. dA is tangent to the disk. No, perpendicular to the disk. In this flux integral, we have a disk, and dA is perpendicular to the disk. So there's dA in the z direction, and b is in the z direction. So b dot dA will just be beta t dA, and the integral dA will just be the total area, A. The area of a circle, or the area of a disk, is pi r squared. So there's the flux. And Faraday's law says the circulation, that's 2 pi rho f of rho, is minus d phi dt. So that'll be minus beta pi rho squared. And the solution is f rho is minus 1/2. And solve this for f. Just divide both sides of the equation by 2 pi. The pi's cancel. I got minus beta, I also have a factor of rho. I have minus beta rho over 2. So that's the answer to the problem. E is in the negative phi hat direction times beta rho divided by 2. Or here's the electric field shown in 3 dimensions, where z is pointing this way. And there's a changing magnetic field pointing in that direction. So the change in the magnetic field points upward. The right-hand rule, the negative right-hand rule, implies the electric field curls around in this direction. What's that? Counterclockwise seen from above. Now how do we know this is all correct? We know by experiments. How do we know anything in physics? We know by experiments. First experiments done by Faraday. As a magnet moves towards the coil of wire, there's an induced electric current. We can measure that with an ammeter or a galvanometer. And we find that when phi changes, there's an EMF around the coil of wire, which drives a current. That current causes a deflection of the galvanometer pointer. So that's where Faraday's law comes from. And now we have also the equations. The rate of change of phi is the negative EMF. Well, this all seems very abstract and kind of mathematical and sort of based on laboratory experiments. Is it important? This is one of the most important phenomena in all of science because of its applications. And in particular, this is the way we make electricity. Well, we can make electricity using batteries, but batteries aren't very powerful. If we all had to depend on batteries for all the use of electricity, we would be much less able than we are. So let's see how we make electricity. The fundamental principle of an electric generator is shown here. We have a coil of wire. It's shown as a little square loop or a little rectangular loop. We have a magnet. It's shown here as the two poles of an electromagnet. So, you know, the electromagnet, of course, the electromagnet has to coil around. So we have a horseshoe-shaped magnet. And there'll be a north pole and a south pole. So that's what we have. We have a rectangular loop of copper, and we have a horseshoe magnet. Now, take that rectangle and rotate it around the axis, the central axis of the rectangle, where the rectangle is in the region between the north and south poles of the magnet, of the horseshoe magnet. So we have a magnetic flux, which flows from the north pole to the south pole. We have a wire loop. Think of it as a loop of copper or something in the shape of a rectangle. And we spin it around. In order to spin it around, we have to drive it. In other words, we have to put a crank here. So we put a crank here. And we take a hold of the crank and we crank it. And we make this, I guess we make this rotate in this direction. No, axis of rotation. It's rotating in this direction. Well, you see, there'll be flux through the rectangle. In this orientation, the flux through the rectangle is 0. Because the magnetic field doesn't go through the rectangle, it goes over and above and below the rectangle. But after I turn it by 90 degrees, there'll be the maximum flux through the rectangle. So the flux through the rectangle is going from 0 to some maximum value as I crank it. Continue to crank it. Well, at some point after it's rotated by 180 degrees, it'll be again lying down in the magnetic field. The blue side will be on the left, the red side will be on the right, and there'll be no flux. So you see the flux is going from 0 to some maximum value, back to 0, then to some minimum value as I continue to crank it until it's standing upright in the magnetic field. It'll have a maximum flux, but in the opposite direction. So you see, you have an alternating flux through the conductor, through the wire loop. Now, if you attach the ends of the rectangle to a couple of slip rings, have to be sliding contacts, and you connect a circuit to those slip rings, as the rectangle rotates, the slip rings rotate, there's an alternating electromotive force between these 2 points. These are called the carbon brushes. Those are the electrodes that slide on these 2 slip rings. So if you now attach this to some device, you'll be supplying an alternating electromotive force, an alternating voltage to the device. Suppose the device is a motor. Well, you could cause this motor to rotate. Suppose it's a light bulb. Well, you could cause this light bulb to turn on. So you see, I need a magnet and I need a conducting coil. and I need a way to rotate the conducting coil. I don't get something for nothing. In order to rotate this coil, I have to crank it. I have to produce a torque on the rectangle to cause it to rotate. If I stop cranking, the magnetic force on the copper coil will cause it to stop rotating. In order to continually supply this voltage, I have to continually put energy into the system by doing work. I have to produce a torque through an angle. That's the fundamental principle of an electric generator. As the magnetic flux through a rotating coil varies in time, there's an EMF around the coil. Okay, well that's sort of a proof of principle, but it's a pretty simplified looking thing. You wouldn't think you could get much electrical energy out of that. So let's look at a more realistic electric generator. Everybody has an electric generator. Well, if you own a car, you have an electric generator. The alternator in your car is an electric generator. It's called a synchronous generator. It's got a rotating component, which is called the rotor. It's got a static component, which is called the stator. The rotor consists of a set of rotating electromagnets. And the stator consists of a set of coil of conducting windings, armature windings, windings of wire. All right, so this is sort of the principle. But that looks like a fairly simple sort of thing. You wouldn't expect to be able to get much electrical energy out of something like that. So let's look at something more realistic. Everybody has a generator. Well, no. If you have a car, or if you have a motorcycle, or if you have a scooter, a motor scooter, then you have a generator. It's called the alternator. The alternator in a car, or that's sometimes called a synchronous generator, is an electric generator. It's shown over here. It has two working parts. One's the rotor, which is a set of rotating electromagnets. The other working part is called the stator. It's not rotating, it's constant in space. It's not moving, it's static. It's a set of wire windings, a set of wire coils called the armature windings. That's out here. So you have a set of coils, multiple coils. Those are called the armature windings. In most electric generators, there are three sets of coils that make up the armature windings. And then there's something that rotates. It's a set of electromagnets. Each electromagnet has a north pole and a south pole. So here's one with a north pole and a south pole. Here's one with a north pole and a south pole. North pole and a south pole. North pole and a south pole. This one has, what is it, looks like 5 electromagnets. In a car, you would probably have 3 electromagnets. which rotate around on an axis through the axis of the alternator. Now, unlike this little principle, which shows the windings rotating and the magnets static, in the alternating car, the magnets rotate. And the coil of wire, or multiple coils of armature windings, are constant in space. They don't rotate. But it's it's a principle of relativity. It doesn't really matter if the coil rotates and the field is constant, or if the field rotates and the coil of wire is constant. Well, as this rotates, it generates alternating currents in the armature windings. Now, most of the applications in a car require direct current. So there'll be some set of diodes to convert the alternating current into a direct current. So there's a direct current, a DC, and there's an alternating current, three-phase output. Now, what causes the rotor to rotate? Well, there's a belt which connects the axis of the rotor to the engine. And as the engine rotates, part of its rotation is used to drive the wheels, and part of it's used to drive the rotor in the alternator. And that torque is transferred from the engine, which is burning gasoline, to the rotor via a belt. All right, well, that's the case of the alternator in a car. That's important to everybody who has a car, or a motorcycle for that matter. You have a battery. The battery is a DC power supply. It's a direct current supply. That magnifies, that produces the magnetic field of the electromagnets. And then the output here is a three-phase output, an alternating current, which can be converted back into DC current with diodes. And of course, to avoid depleting the battery, you take part of this output current and you put it back into the battery. So there's a whole wiring yoke which ensures that the whole thing remains working. You recharge the battery with output from the generator. And then the rest of the output from the generator is used for things like lighting the lights and lighting the headlights and all kinds of little motors that are inside the car. Now, you don't get something for nothing. You have to burn gasoline. You have to produce carbon dioxide. The carbon dioxide may produce global warming, but never mind, you want to get from your house to your job, so you drive the car and produce carbon dioxide, which goes out into the atmosphere. But the way it all is possible is because of the electricity produced by the alternator. Oh, why does a car need electricity? Well, the spark plugs have to ignite the gasoline. There's a gasoline-air mixture in the engine that has to be ignited by spark plugs. Where do the sparks come from? They come from the alternator. All right, so this is part one of the screencast, sort of the theory of electromagnetic induction. And now there'll be another part, part 2, which will be some example calculations.